Well, hello everybody. It's Rob here. Hope you're all very well. As promised, I'm going to start doing some tutorials on heating design right the way from start to finish. Now, this is going to be over probably many weeks now to get things moving. There's always new content to kind of add to this thing, and I guess I'll kind of accept people's comments really in the posts and see if there's bits that people would like to elaborated on, those sorts of things, and see if we can move it forward for everybody. I mean, the whole idea is to just try and get everybody, if we can, up to speed with modern day of thinking of heating design, and try to make it as simple as possible. Now, the first couple of videos that I'm going to do with this, I've taught for quite a few years. I've changed the slides around quite a bit and that sort of thing, and maybe some of the descriptions, that sort of thing. But I want to just try and get everybody sort of up to speed on this. And it takes as long as it takes. It's not for me, it's not a problem with any of that at all. And I will always do my best to reply to all comments and get back to everybody and try and help people across the post. So we're going to start, let's say, right at the very, very beginning. And the very, very beginning that you have to do when you're going into a property is get an understanding of what size of heat source you're going to need. And for that, you're going to need to do a heat loss calculation. So what I want to do, first of all, is start on showing you how to do a longhand heat loss calculation. So with pen and paper, a longhand heat loss calculation. And this will... The main reason for doing this, and I'm not out here to cast aspersions on any particular industry or anything like that, but we all know that it's quite tight and it's quite hard, making money in whatever kind of genre that you're in within the industry. And I have found on quite a few occasions that when we get submitted architects' drawings and those kind of things, there's quite a lot of copy and pasting that goes on. And as I say, I'm not pointing the finger at anyone in particular at all, but this is some of the problems that we do find. And so what can happen is that there's two things that you need when you're starting to do a heat loss calculation. You'll need either a good set of drawings or some good software that you can go and do the measurements of a building yourself. Obviously some knowledge of building surveying, so you can recognise different building materials and different types of things, but we'll come on to some of that in a little bit to try and help you get a little bit closer. And the whole point of this is we're just trying to get a little bit closer to the truth. So I did do a video a little while back, a couple of weeks ago now, of a kilowatt hour to kilowatts, where you can literally just take a gas bill and you can look at input all the kilowatt hours that you've had for the worst month of the year. You can then energy divided by time, so you just divide that by the time of the heating that you have in a monthly cycle or something like that, and that will give you a kilowatt rating of what you need. Now, obviously you've got to take things like cooking, if you're cooking with gas, off of those things, but it's an estimate which is a hell of a lot closer to what we have been doing, which is sizing primarily gas boilers 5, 6, 7 times more than they actually ever need to be. You don't need a 40 kilowatt boiler inside a house or a 2-bedroom house that only has around a 3 kilowatt heat loss. It's as simple as that. So we're just trying to get a little bit closer to the truth. So the two things that we really need when we're starting to do this is we need some drawings. So PDF drawings or CAD drawings, whatever it is that you can get, but it's really important that you get from the architect or your client the construction notes. If you get the construction notes, I would then ask for these construction notes to be confirmed in writing that the architect is happy with those construction notes and the U values that are supplied by this architect are correct, and you can use them within your calculation. The reason I say that is that we live in a very, very litigious kind of society now, and you just need to cover your back, that's all, with this. But what I would always say is that to do these longhand calculations is something that everybody should know, and you will do after this. They'll be there forever, and you can just download this video and reference it at any point you like. But the point is, this gives you the tools to very, very, very quickly check an architect's drawings, check the construction notes, check the building materials that have been used on site are exactly the building materials that have been used when the drawing was designed or when the building was designed, and then you move forward from there. So this just gives you those tools. And many times I've sat in with meetings with clients and architects and I've found faults and problems. And the point of this is that if you install a heating system, and a low temperature heating system in particular, and you get it all up and running, and then 6 months later the client says, well, it's not achieving set point, or it's not doing the things that it is doing, You say, well, I've done the heat loss calculation to the information that you gave to me, and then it turns out that the different building materials have been used, or it's not been installed the way it should be. They're going to come back and they're going to knock on your door. And my whole point of actually giving this education out for free these days is just to make sure that you're armed with all of the tools you need to go and do proper low temp design without any worries. All right, so I think let's crack on, see how we go. See, these will be shut down into shorter videos, 20, 30 minutes, maybe 40 minutes, something like that, to get past the post on each point. But I can't do all of it in one go because everyone will just die of PowerPoint death, basically. So there's a couple of things that we need to see on this. These are thermal conductivity values. Now, this is a page that is taken straight from the CIBSE book, but you can go in and you can just freeze this or stop this video as it stands now, and then just write down this address and go through there. There's thermal conductivities lists are everywhere. Now, there is a regulation in the UK. I'm not sure what the regulation is, but there is a regulation in the UK that states that any building material that is sold within the UK that is of construction purposes, like timber or brick or block or plaster or whatever, has to have a thermal conductivity value added to it, which makes sense. Because then you can choose different things, and unfortunately, as you can see from the bottom here, what I'll do is I'll just pull up the slide of this, which is blown up, so you can actually have a proper look. But you can see, like for argument's sake, there are loads and loads of different types of block, of concrete block, brickwork blocks, autoclaved aerated concrete block, which is like a thermalite block or a Celcon block, and they all have different conductivity values, as you can see down here. And this is the column that we are concentrating on, which is the column in yellow. So you can see they've all got different values, and this can make quite a big difference in your calculation if you're not careful. As I say, we're only trying to get closer to the truth, so we can round up some of these figures to get to what we to what we need. So that's a very, very important chart. Again, you can do what I probably would do is either go to this website here and download this, get the CIBSE book and download that. You can get it on PDF version as well, or just stop this video, as I say, where it is now, and take a screenshot of that section there, and then you can blow it up and you can use it forever. Keep it on your phones or your tablets or something like when you're out on site, and you just got a reference point there for just looking up certain materials and seeing what the conductivity values are on those. So, first of all, we need to understand what is heat loss. What is heat loss and what are we trying to do? Well, heat loss is the energy that is lost through a building fabric in real time, depending on what the outside temperature is doing. So the more heat loss you have, the less of the resistance you have within your building materials and your building fabric. So it's our job to try and calculate those out. And it comes out of things like doors, windows, floors, roofs, walls, all sorts of things like that. And they all have different values to them. And this is what we're going to discuss in this little section. Very, very basic. This is a real good introduction to this, and a lot of people, a lot of you engineers know it. I just think this is a very, very good reference point to start. There's also a lot of people that don't know this, so that's why we're doing it. So bear with, please. First of all, we have to understand a couple of things here. You will often see on drawings, on builders' drawings, etc., heat that is done in Kelvin. And what we need to understand is what that figure of minus 273.15 actually means. Well, we won't dwell on it too much. This is absolute zero. This is absolute. So Lord Kelvin actually worked out that you cannot extract energy. You cannot extract energy out of anything at a temperature down at minus 273.15. So it means that anything above that temperature, we can extract energy from, which is why we've got heat pumps at the moment that work right down to minus 20 or minus 30 degrees outside. They can still take energy from that air or ground, whatever, as long as it is above minus 273.15. So it's absolute zero, or the engineering scale is 0 Kelvin. So all that really means is that Kelvin starts at minus 273.15, and that is 0 Kelvin. So all you really need to do is add 273.15 to any temperature in Celsius, centigrade, and you will have the number in Kelvin. So you will often see, something along the lines of 320 degrees K or something like that for a boiler flow, or something like that for a boiler flow temperature. So that's just a very, very simple calculation of how you do it. So just all you need to do is remember the minus 273.15 as being your 0 point of Kelvin, and that's it. Now, this is where we start to get into the figures. These are the three major components that you need to understand when doing longhand heat loss calculations. So we need to know these three things. We need to know the resistance of the building materials, which is the R value. We then need to know the conductivity, or the thermal conductivity of the building materials, and that's your K value. And then what everybody's probably heard of is the overall heat transfer coefficient of both the R and the K values, and that's the U value. And I'll show you how you can manually calculate a U value out of any building material whatsoever, and it is so easy, guys. Everybody can do this. So, with resistances, we need to start looking at some figures. We need to know what a number means, what a resistance in meters squared Kelvin per watt, what it actually means. Now, if we look at these different three typical constructions, okay, we've got an aircon wall section here, we've got a wood section, okay, and the R values are different. You can see we've got 9, 11.5 and 13.1. So what we need to know is, what is the resistance that we want? Do we want more resistance or do we want less resistance? Well, the obvious answer really is we want more resistance. So the higher the resistance value, the better the construction is for heat loss, or to mitigate heat loss. So in this particular example here, where the cursor is that we've got an R value of 13.1. And I'll show you how to calculate these out in a second. But so that masonry section is obviously the best construction for less heat loss through a building fabric. So we could, for argument's sake, we could add a wall section, a wood section, up to that masonry section. And then you could do 13.1 plus 9, because that becomes a single construction. But we'll come on to that and those mathematics shortly. It's really, really quite easy to do. Now, the law of thermodynamics basically states that hot will always go to cold, or it will always try and find equilibrium. So this is the thing. So if you are, if you go outside without a jacket on or something along those lines, and it's freezing cold outside, you will feel cold very, very quickly, because you don't have any resistance fabric on top of you to resist that heat loss and keep you warm. Exactly the same thing it goes on with buildings. Now, the law of thermodynamics, the second law of thermodynamics, means that hot will go to cold in any direction. Doesn't matter whether it's north, south, east or west or whatever. So a lot of things that people tend to miss or forget when they're doing these calculations is what's happening with the floor in buildings. Has the floor got insulation in it? Is it just a solid screed floor? Is it a suspended floor with lots of air movement underneath it and then not insulated? It's a very, very big subject, and as I say, all we're going to do is get closer to the truth with this description. It's up to you to find out what the floor makes up. The floor makeups are. In fact, all of the constructions, it's very, very important that you find out what they are. And we'll come on to some of those and ways of actually identifying what they are shortly. But so in theory, I'm not sure if anybody has been or gets involved with camping, going camping, especially when the weather is cold. One of the most important places to actually put insulation is underneath you. I do a lot of motorbike camping, and I've got a mattress, a blow-up mattress, which I do, that's got an R value of 6.8, I think it is, something like that. So I've got quite good insulation, quite good resistance between myself and the floor. If you start putting fabric or extra clothes on, or another blanket or whatever it is over the top of you in a scenario like this where you're losing heat straight through the floor, what you'll actually do is you'll start sweating inside that sleeping bag or inside that thing, and this is what can happen within buildings as well. So it's really important to understand where these heat losses are going. I've actually typed on there, as you can see, what happens if you fill a balloon up with hot energy. So if we always say that hot will always go to cold, think about this as a theoretical point of view, because it generally won't happen. If you've got outer space, which is at 0 Kelvin, so minus 273.15, but in theory, you had a ground temperature that was colder than the air temperature, and you held a balloon with hot energy in it, so like, if you let go of that balloon, it would actually fall to the ground, wouldn't it? But of course, it doesn't, because we know that it gets colder the higher you go up, and so hot will always try to go to cold, which is why the lucky people in this world can have champagne balloon rides and that sort of thing. But that is your second law of thermodynamics, and we're taking advantage of that with this sort of thing. So it's very important to explain this resistance through building materials, and we have to mitigate that resistance as much as we possibly can and fight that second law of thermodynamics. And the second one that we've got is the K value, or lambda value. I'm sure people have heard of lambda value before. And this is your thermal conductivity. Very important to understand this. Now, we've got two things. We did say just a minute ago that we wanted very, very high resistance values as much as we possibly could, because we want as much resistance to the second law of thermodynamics as possible. But conductivity and K value, this is the rate or speed that temperature difference occurs on different sides of that building material. So it's the conductivity is how quickly the energy moves through the building. So we actually want the opposite of the R value number. We want the lowest possible conductivity value that we can. So the lower the conductivity, the slower the rate is of temperature change. So this is very, very important. And as I say, these conductivity lists, you have to do a simple Google search on conductivity values, and there will be absolutely loads that come up. So you can easily identify different conductivity values. And the last part on this point is that K values, they're measured in watts per meter Kelvin. So with conductivity, as I say, this is just another added explanation as to why we don't want good conductivity in building fabric. You take something like this, we all know what it is. It's a resistor that is built into an electrical circuit. That wire or that cable on its own, if it didn't have that resistor in it, there'd be really, really good conductivity in it. It'd be sending too much energy through to the point of its end point, basically. So we put these resistors in, and of course they're all different color coded for different resistance values to them. That is basically a bit of insulation. So that's a bit of insulation in your building materials, in your cavity wall or something like that. So we want as much of that inside a building material as we can. It's all about getting the right conductivity, or the least amount of conductivity within our calculation. So this really explains itself. We don't want communication between inside and outside. We want to do our best to limit it in regards to heat loss. So very, very important. So a high R value we're looking for, and a very, very low K value. So we'll check on those in a minute, and we'll see what we can do with those and start making some calculations. So we then have our third point, which is a U value, which is the overall heat transfer coefficient of the both R and K values. So this is what we need to do in order to ascertain exactly how much heat is being lost through a building fabric at any one time, depending on the outside temperature outside. But again, we'll come into more of that and get into more depth as we move forward. So just a little reminder, this is what these values are measured in. So the R value is measured in meter squared Kelvin per watt. The K value is measured in watts per meter Kelvin. And the U value is measured in watts per meter square Kelvin. So this is where we now start to think about using calculators and getting our first calculation out of the way. So to find any resistance of a building material, we start with thermal conductivity value. And if this thermal conductivity value even is out of all of these building materials, so walls, surface finishes, roofs, floors, insulation. Okay, and we said we want on this line in this yellow column here, we're looking for the lowest possible number, and I'll come on to some of those in a second to give some examples. So all we need to do to find the resistance of any building fabric, we divide the thickness of the building material, but we want that thickness in meters. It's very, very important. So we want that thickness in meters. So for argument's sake, if it was 300 millimeters thick, the equation would be 0.3, because that is 300 millimeters. to within 1 metre. If it was 30 millimetres thick, then we would be looking at 0.03. So it's all about getting your decimal points in exactly the right place. So if you had 3 millimetres of skim plaster, for argument's sake, that would be 0.003. That's very, very important to understand the decimal points within 100 or 1,000 value. So we have the thickness divided by the K value, thermal conductivity. So thickness in metres divided by the thermal conductivity, and that gives you your R value. And the resistance, again, measured in metre squared Kelvin per watt. So thickness divided by conductivity gives you your R value. So if we are in this thermal conductivity values, we can take some typical values and we can just have a little look and see what we've got. So if we look at a really, really bad K value, and we can see that we've got one down here, like there's stone granite there, stone granite at 2.93. And look how much higher that value is to everything else on this list. It's huge. So we know that there's an awful lot of buildings in the UK that have got very, very thick, 600, 700, 800 millimetre thick stone granite walls. And they are very, very hard places to heat. They hold a lot of thermal energy in the actual building material itself after a time, but it also loses it quite quickly because of its conductivity value. So this is something that we try to mitigate and try to understand. So you look, then we come down to our insulation levels, and look, you've got some of these, we've got very, very low insulation levels. So that's standard PIR, which is Celotex or something along those lines there, like 0.022. So it's very important to see these different conductivity values. And remember, it's the thickness in metres. So for argument's sake, if that was brickwork outer leaf and it was 0.84, a brickwork outer leaf, the brickwork is generally 100 millimetres thick, so it would be 0.1. So thickness would be 0.1 divided by the conductivity, which is 0.84, to give us our resistance. So let's do some more of these. So pause this one anytime you like. I'll get the calculator out in a minute and we'll try a few and see, so everybody's up to speed with looking at these very, very basic principles of heat loss. Now, there are a couple of other things that you need to think about. And CIBSE have decided that whenever heat from the inside hits a surface area, there is a constant value of resistance that has to be added onto every calculation that you do. Now, most software will add this in straight away, but they are called surface resistances. So I want you to imagine that this is just a standard cavity wall. That's your inside block work, that's your cavity wall insulation, and this is your outside brickwork. Now these surface resistances have to be added onto everything, and you can see we're just adding on 0.18 in total, so it'll be 0.12 plus 0.06, which is 0.18. So that is a constant in all of our calculations that we do, so we really need to add on those as we go forward. So let's do the calculation. Let's say we have a building material thickness of 20 millimetres lightweight plaster. And lightweight plaster is something like, bonding or hard wall or something along those lines. So the CIBSE guide for the K value for lightweight plaster states it's got a K value of 0.18. Well, let's just double check and see that it has. So it's a surface finish. Yeah, lightweight plaster. There it is. Look, 0.18. So it's 0.18 on our calculation. So if we bring up our calculator, just so we can prove that this is the way forward, and this is exactly right. Let's just make sure that's okay. So we're looking at a K value of 0.18. Now it was a thickness and it was 20 millimetres. So 20 millimetres in metres is 0.02. So the equation is going to be 0.02 divided by the conductivity, and it gives us 0.11 of resistance. That's our R value. So let's just try it and see what we've got. So we've got 0.02 divided by 0.18, and there you have it, 0.11. recurring. So very important to try these, get the calculator out and check them out. So as far as we've got now, we've already established how to find out what our resistance value is of any building material that we've got. So it's thickness in meters divided by the thermal conductivity of the building material, and that gives you your R value. So let's move down from here a second. Now, all of these have different levels. So we've got our surface resistance that we said, which was inside of 0.12. That's our surface resistance. We've just done our 20 millimeters of plaster, and that's 0.11 as we've worked out. We can look at a block. A block was 100 millimeters. Now let's see what that is. So we've got 100 millimeters. Let's see what the conductivity value is of it. Yeah, I think I used with this one. I think I used an autoclaved aerated concrete block, which is 0.18. Okay, as a conductivity value. So let's go back to this, and we've got a 100 millimeter block. So we would have 0.1. That's your 100 millimeters of block divided by 0.18 equals, right, 0.55. So we've used a different block there. We've probably used a concrete block. And let's just find out whether we have. So let's use a concrete block, a dense concrete block, which has got a very high, yeah, let's try that one there, 1.4. So if we've got 1.4, we'll come back again to our calculator, and we've got thickness divided by conductivity, so it'd be 0.1, which is your thickness. If it was 100 millimeter thick, divided by 1.4. Okay, so that's 0.07 of resistance. So so we've used something that is in between there, in between the two, to get that figure. But you get the point. Calculators don't lie as long as you input the correct data. Simple as that. Then we've got some insulation, which is our 150 millimeters of insulation. Then we've got our outside brickwork, and that's our R value for that. And then plus our outside surface resistance. So for this typical construction of a cavity wall, a standard cavity wall, we've got a resistance value of 4.85 meter squared Kelvin per watt. Forget these inside and outside temperatures for the moment. We'll come on to that in the next section to this. So I hope everyone understands that little bit there. So that's very, very easy to find your resistance value, your R value. Thickness divided by your conductivity gives you your R value. And what I generally do is make up a simple basic chart of this. So you have your indoor constants and your outdoor constants, which there. So that's your indoor constant of 0.12 with R value. That's your outdoor of 0.06. So we're adding those onto every equation that we're doing. And then these are, so you've got your different building materials all the way down here, which you can easily make up. Then you've got your thickness in meters divided by your conductivity, and that gives you your R values. Add them all up, and away you go. Now, this little symbol here is basically it's a sign. It means the sum of. You'll see it in some equations. It just means the sum of. So when we want to convert a resistance value to our U value, remember we said that it's meter squared Kelvin per watt, and we want to turn it around to make it watts per meter squared Kelvin, which is basically flipping the equation just upside down. All we need to do to that, or to get that figure, is divide the number 1 into the sum of all the resistances. So the sum of the R, sum of all the resistances. So that is the equation there. So we had 4.85 meter squared Kelvin per watt in our sum of all of our resistances. That's the total lot there. So in order to work this U value out, we say 1 divided by the sum of all the resistances of 4.85. And let's just make sure the calculator is not lying. And let's do it. So we say 1 divided by 4.85, and that gives us 0.21. Why is it 0.21? So it's 0.21 because we always take that third decimal point there, and because it's over 5, we round that up. 0.21. That is watts per meter squared Kelvin. And we'll come into what that all means in a minute, but that's now losing 0.21 watts per meter. Now, we've only just calculated the watts per meter square. We need to now calculate a whole building construction for that type of building construction within a room or a wall, that kind of thing, assuming the walls are all made of the same construction. There might be different constructions which you'd have to add on, but again, we can talk about that in a minute. This is why software is so important, because it makes it so quick to do. This is just a simple way of learning the longhand maths and making sure that you are able to look at a set of builder's drawings and make your decision about how to calculate these out. Okay, so recap. Thickness divided by conductivity gives you the R value, or the resistance. You add up all the resistances, you divide the number 1 by the total sum of, or the sum of all the resistances, and bang, you have your U value. Easy, real easy. This will make life very, very easy for people to do. And I say, I always check builders' drawings whenever I see them, and generally I will find 1 or 2 mistakes. And again, 9 times out of 10, it's probably not the architect's fault. It could even be the builder's fault that has built this project, who has seen that there are a cheaper version of the product that the architect has specified, and they've just gone with that particular block or something like that, and as we've seen, they've got different K values, and so therefore the equation is different, and this could make quite a big difference on your overall heating design, which is why we have to be very, very careful. Now, the importance of insulation. This is a kind of story that I've been saying for many, many years, but it's still relevant today as it's always been. Now, if there are any installers out there who are listening to this, and you've gone in to fit a boiler or fit an air vent in a wall, an extraction vent, or anything along those lines, where you've actually had to make a penetration into the exterior wall, you get your core drill out and you start to drill a core through the wall. You set all your steps up. You might have marked up all your template for your boiler or whatever it is that you're mounting on the wall that needs that. Or even you might be fitting a heat pump, and you might be bringing in some primary pipe work that is insulated all the way through the wall, as it should be. You take your first drill through the wall and you hit the cavity, and without thinking, you pull that core out, and before you know it, you're knee deep in snow, or knee deep in polystyrene balls, as we've all seen before. Now, that is compromising the integrity of the resistance value of that product. You imagine if you're right above that hole that you've just made in the wall, you will have created a massive V shape where all those polystyrene balls for meters and meters and meters above in that cavity have just drained out into this Y-shaped funnel look as it's all poured out of this hole in the wall. So I would always suggest, whenever you go in to do any work or penetrations into any wall or construction of any building, is I have a little selfie stick which I put on the end of my mobile phone, and I will get up into the loft space of each building and I will check. I'll also look on the outside and just make sure and have a look and see if there's been any drill holes or anything on the outside where it might have had phenolic foam pumped into the building or something along those lines. But speak to the clients, find out what the wall makeups are, but get up into the loft spaces. Put your phone on your selfie stick, put it on video, and put the light on, and just poke your video down into the eaves of the construction, and you can have a quick look down the cavity to see what it is. And if it is polystyrene balls, then I would do 1 or 2 things. You've got to try and maintain the continuity of that insulation. That is the most important thing that you can do, and I'll show you why in a minute, of how much heat we actually can lose out of these things with calculations. So what I would do is take a bit of that insulation that guy there is demonstrating, and you can, they're just cavity wall bats that you've got there, or main insulation there. You take a piece of that and make it into like a 4-inch gasket or something along those lines. That's as thick as the cavity with inside, so 100 mil thick or something along those lines. You then very, very carefully core out the inside skin or outside skin, whichever way you're going in first. And then as you take that core out, have that gasket ready to put in immediately. You will lose, less than a couple of handfuls of the polystyrene balls, but you push that in there, push it into the cavity, and push it all around so that maintains the integrity of that insulation. And then you can drill your second lot of core out, and then you've maintained that right the way through. So a real good tip to do that and make sure that you keep the heat and keep the maintaining of the resistance value, the R value of that typical construction. And we'll do a couple of calcs now to see what happened in this instance and what can happen. So if we removed that insulation out of this equation, what happens? Well, let's have a look. So we take that 4.28, which was there for that insulation, we take that and we subtract it off of our total that we made up. That means we've only got a total resistance value of that wall construction then of 0.57 meter squared Kelvin per watt. Now that's huge. So if we now convert that to a U value, 1 divided by 0.57, we're now losing 1.75 watts. So we look at this again and we'll do the comparison. So with insulation, we were losing 0.21 watts of U value. And then without insulation, we're losing 1.75 watts of U value. Now this is quite a lot, and this is why it's really important to understand these basic physics, if you like, of how heat moves in real time from a building. We've got to try and mitigate that as much as we can. I know I keep banging on about it, but it's very, very important to get this across to people that insulation is incredibly, incredibly important. So we are literally heating the sky there, and total unnecessary emissions, all sorts of things like that, all because we didn't mitigate the heat loss of that wall construction by putting in an insulated gasket to stop all that snow falling out, or recognizing what the insulation was within that wall construction before we drilled through it. So preparation, preparation, preparation. 1-1-1 principle. This is really quite important to understand, because we now have a U value of a construction, of a wall construction. Now again, these can be walls, floors, roofs, doors, windows, all sorts of things like that, but we can go into more detail on what they are. This 1-1-1 principle is very, very important to understand. And what does it mean? What it means is, if you have a U value of 1, that means that 1 watt will be lost through 1 square metre of the building fabric for every 1 degree of delta T. Now delta T we'll come on to in a second, but what does it mean? Delta T means the difference in temperature between inside and out, or flow and return. If you've got a delta T of 10 for argument's sake, it would mean that your heating system for argument's sake would be 60 degree flow and 50 degree return. That's a DT of 10. So we have to now look at this third equation, which is really important. Well, it's a fourth equation, isn't it, really, after that? So we've done thickness divided by conductivity, gives us our R value, add up all the U values, divide the number 1 between the total sum of all the resistances, and that will give us our U value. So we now have to do, for an area of a wall, for argument's sake, we have to measure that out and check, or a floor, we have to do U value times area times delta T, and that is your 1-1-1 principle. 1 times 1 times 1 equals 1. All right, so let's work it out now with a bigger wall area. So if we've got a wall area, and let's just say we've got a wall area of square meter area of 10 square meters. 10 square meters, and we've got a delta T of 23. What does a delta T of 23 mean? Well, it means that if we're designing to SIBC guidance at the moment, or modern ways of thinking of designing to internal room temperature, we're looking at internal room temperature of 21 degrees. So at 21 degrees internal temperature, that would mean that our DT of 23 there means that we've got an outside design temperature of -2. And delta T you'll often see written down exactly like that symbol there, delta T. So this is where you've got 21 degrees inside, and minus 2 outside. So it's literally 21 plus 2, that is your delta T, and that is how we describe it in this scenario. So it could be anything. You could be working in a care home or something that wants 23 or 24 degrees, and you might be, up in the north of England somewhere where the outside temperature is minus 6, for argument's sake. So if you've got 24 degrees inside and you've got minus 6 outside, you've actually got a DT of 30 that you're working to. So let's look at these two calculations, as we said, one with insulation and one without, and let's see what difference it's going to make on a 10 square metre wall. So before we do that, we have a thing in the UK, it's called degree day data. Now this is based from CIBSE. You can check out the link at the bottom there, degreedays.net, to get a free calculator for this, which is really, really good if you need to do bespoke calculations. Most software has it built into it, which is just postcode and that sort of thing. So you find out what your degree day data is. Now, good degree day data, it's very important to understand that CIBSE, or the guidance that we have within the UK, and this is all around the world as well, will generally work on an outside temperature when you require heating. So they work on degree day data of over 15.5 degrees Celsius. What they're saying by that is that over 15.5 degrees Celsius, you don't require your heating to be on. But anything underneath 15.5 degrees Celsius, CIBSE are assuming that heating will be on in order to run your property up to your internal design temperature of 21 degrees or whatever it is that you want to do. And that kind of makes sense. We do have, and it's a caveat here, we do have some of the worst performing buildings in the whole of Europe. And it's pretty embarrassing, really, for what an industry that a lot of us have been in for many years. We actually lose around 3 degrees in every 5 hours of building fabric in the UK. Now that's very poor when you start looking at some Scandinavian countries that only lose around 1 degree in every 5 hours. And France I think is about 1.5 or 2. Belgium, I think, is about as bad as we are. That's about 2.5 or something like that. But they've also got very old building stock. So it's really, really important to understand what you're designing to, and degree day data helps you. We also need to understand that we used to design to different temperatures inside rooms. We used to multi-zone or micro-zone in areas, and you can see from the slide here that kitchens, halls, utilities, landings, etc., we'd always design them at 18 degrees C. Lounges 21, bathrooms 22, which we still do. Cloaks, WCs, that sort of thing, 18 degrees as well. Well, we know from our previous slides, the second law of thermodynamics, that hot will always try and find equilibrium to cold. So now in modern heating design, we generally design to one temperature right the way through, because people leave doors open. If you can shut doors and you can prove that you can't, you've got good resistance within that door fabric, then fine, you can design to different temperatures if that's what you want to do. But those doors need to be shut in order to stop hot going to cold, and that's second law of thermodynamics. It means that if you're designing a radiator for your lounge, in this instance, and you're designing that to 21 degrees, if the lounge adjoins to the kitchen and you've only designed the kitchen at 18 degrees, it means that radiator from the lounge will actually be undersized, because it is missing out on 3 degrees and it's trying to heat the kitchen area because it's open up to 21 degrees as well. And of course that means it's undersized because it's only designed for the size of that particular room. So this is why we're trying to design everything at 21 degrees these days and actually have good modulation controls and nighttime setbacks, that sort of thing. Makes it easier for the maths as well, to be honest. So if you remember, we had two calculations of U values, one with insulation and one without insulation. So we do our U value times area times delta T calculations twice here, and the initial one that we had was 0.21 up the top here, times 10 times 23, and we've got 48.3. Well, let's just double check and make sure that we've got this right, just to make sure that the math, the calculations are good and the mathematics are correct. So we've got 0.21 times 10, which is your U value, times area, times your delta T of 23, and we'll get 48.3. So we're losing now out of that 10 square metre wall, so one whole wall with insulation, we're losing just 48.3 watts. That's quite scary, isn't it? And now when we look at with the insulation, where you've got maybe 5, 6, 7 dustbin liners full of polystyrene that you can't put back into the system unless you get back up into the loft space and actually pour it back down the cavity above where you've made your hole, you're going to be in some problems. So we're now losing nearly half a kilowatt, 400 watts out of that wall, all because we didn't do our due diligence and check that insulation within that wall. And I'll be honest with you, I've made the mistake. I've been in the industry for 43 years as installer and everything. I've made the mistake of actually doing that, and it kind of does send you into a bit of blind panic sometimes because you can't stop it. Now we've only created the U value, or calculated the U value out of one area. So we now need to add up all the areas of walls, doors, windows, roofs, etc., and use the same U value calculation process that we've just done. Now don't overcomplicate this thing. Do one construction at a time and just check what it is. So do your walls, then do your floors, do your windows, and just check online for some of the latest guidance on what the conductivity values are and what windows are. Like, for argument's sake, modern windows now, they are deemed to be, well, the UK building regulation currently, as we stand in 2025, is 1.6 watts per metre squared Kelvin as a standard window installation. But you can easily buy 1.4 U value, so a lower U value, which is exactly what we want. We're looking for a nice low U value for our heat losses, and all we're trying to do as heating engineers is replace the heat that is being lost constantly out of that building fabric at whatever the outside temperature is to maintain our indoor set point. So very, very simple. Look at it methodically and logically as you design these or calculate these U values. So if we had a lounge, for example, and that had in total 67 square meters of wall space, we do the U value times area times delta T calculation again, and you can see from this one, for that whole lounge, we're losing 323.6 watts of fabric heat losses. Now I'll come on to that in a minute, and that's going to be for another video. Most important thing is to understand the U value times area times delta T and recap of your thermal conductivity values, which is your K value, and your resistance values, which is your R value. Now, this is the last bit for this video, but I want to discuss this because this is really important to leave this on. Now, this was a live project that I did. Not these houses. That's just a stock image. But this was a live house a live project that I did, and this was a 1930s built house, quite poor insulation, and we can see from a few little points here. You know, these walls that I had 257 square meters of walls. The U value was 0.21, but that gave me a total fabric heat loss in that. So U value times area times delta T of 1241 watts. Now, this client said to me, am I eligible for the £7,500 grant money? And I said, well, yes, you are. But I've got to go and do my due diligence of doing a heat loss calculation to see whether there is anything that this client should be doing before we move further forward with her application, etc. Now, look, we can look there at two really, really big areas of problem within this building. And I did a full survey there. I poked my head up in the roof. There was basically no insulation up there whatsoever. And there's 180 square meters of it, as you can see from this point here. So we had a U value of 2 on that. So 2 times 180 times 23, which is your delta T. We are losing nearly 8.3 kilowatts out of that roof space. But look at the windows. The windows weren't changed from day one when that house was bought. So they were single pane sash windows on there. And that 4.8 is arguably too low. That should probably be higher. That should probably be around 5.6 or even 6 as to what that you would be losing in terms of U value. But again, that can be calculated. We've shown how to calculate a U value now. But there's some low-hanging fruit. So this client said, is this property, can I have a heat pump in this property? Now, my answer to her was very, very simple. No, not yet. You could put in, and this is an argument I've had for quite some time, because you've got a total here. When you add all of these total heat losses up with this, you've got a total of 17.9 kilowatts, as we can see down the bottom here. So 17,951 watts that building fabric, just the fabric heat loss, is losing from that particular building. That's quite scary. So what I want to do is just spend 3 or 4 minutes here before we finish this video and just go through a couple of things that we could do. Now, if we said to our client, right, well, how about we put some insulation in the loft? Well, the first thing we've got to do is we've got to work out what, if we put 300 millimeters of insulation would be in that loft space. So let's have a look. So we pull up our conductivity. We'll scroll all the way down to insulation and we'll look at mineral wool quilt. Okay, which is kind of what you would use, the rollout stuff that you would use inside a loft space. You could use PIR if you wanted or whatever. That's just a lot harder to install. So mineral quilt insulation takes us down, gives us a conductivity value of 0.042. So let's have a look and let's calculate out the R value of that and convert it into a U value. Again, we've got to go thickness divided by conductivity, and if we put 300 millimeters up there, we have 0.3 divided by 0.042. So it's thickness divided by conductivity equals, now this should be a fairly high number now. Yeah, so we've got 7.14. 7.14. We don't bother going any more than that. We don't need to do that. We only need about two decimal points really. We use the third decimal point. If it's over 5, then we'd round this one up and work from there, as we said. So 7.14. So how do we get to the U value again? Well, very simple. We just go 1 divided by 7.14, and that equals B. So we've got 0.14 now. So we're all agreed on that. So we go 0.14 times 180, which is our square meters, and then times our delta T of 23. And we're now losing just 579 watts out of that. We could call it 580 watts. So we're losing 580 watts as opposed to 8.3 kilowatts. So we're now losing 580. So let's just add that down. I've just written that down there. So it's very simple for you to do at home and calculate these out. So that's one point that we've got an issue with. Let's have a look at the windows. So she's going to change the windows. And they were going to do this anyway. This was part of it was in their budget of their upgrades that they were going to do. So that was fortunate. But these windows, so we've got 4.8 at this. Now, if we go to the standard building regulation at the moment, which is 1.6, let's work that out. So we've got 1.6 of a U value times, we had 56 square meters, times your delta T of 23 equals. So we're now losing 2 kilowatts out of the windows as opposed to 6.2 kilowatts. So we've got 2060. Right. Now we're getting somewhere. So if we now add all these up, so we've got 1241 plus 699 plus what was it, 2060 plus 1104 plus 580 is all we had on that, 580 watts, plus your last one of your doors, which is 445. So we are now losing on new heat loss on the fabric heat losses are just over 6 kilowatts, and that's just by insulating the roof and by changing the windows. So we've gone from 17.9 kilowatts of heat loss down to 6.2 kilowatts, 6.1 kilowatts, so just over 6 kilowatts. Now that is pretty epic, and I think anybody can see that just by doing some longhand heat loss calculations on a building fabric. Now, is that building now heat pump ready? Well, yes, of course it is. And that's going to be perfect. That's going to run at a wonderful, wonderful low temperature system for these guys. So that is what I class as doing due diligence on a building when you're doing a survey, to make sure that that survey is absolutely correct. So there you go. This is why I think it's very important to do these first of all, and pass on to onto your clients. Plus, it gives you credibility as a bona fide and a competent installer. So, is that it? Well, no, it's not. But this is where we're going to end this particular first video of this tutorial. To say, I don't want to go on and on and on and on with each individual. This has probably gone on long enough as it stands now, and I think it's too much for people sometimes to do. So I really hope you enjoy the video. Please give it a thumbs up. Hit the subscribe button if you don't mind, and hit the bell icon as well, so it will let you know when a new one is coming out. I'm going to try and get a few done fairly quickly. At least one a week at the moment for what we're doing. But yeah, I really hope you enjoy it. Put the comments in below. I'm on various different channels now, so I've got my own YouTube channel. I'll put it up on all of my other social media links. I've got a Facebook channel as well now, which has just been set up recently. So you'll find all of these videos on these. And yeah, let me know what you think. Many thanks, guys. Bye-bye.